What's up? Y'all ready to go to infinity and beyond? Which is still infinity? Question mark? Because that's where we're going. We're gonna put horizontal asymptotes in a new question, basically. So, what happens as x approaches infinity? This is basically asking the same thing as what is the horizontal asymptote? Okay, limits at infinity is the section in the book. That's what it's called, limits at infinity. But technically, it's more like what's happening as x gets bigger and bigger and bigger, or as x approaches infinity, which turns into what are the horizontal asymptotes. So the good news is this video will be really, really short because we've already talked about horizontal asymptotes, right? How do I find the horizontal asymptotes? What are what is, how about that? Let's make it singular. Like things are written in the plural, like limits, plural, but really each question's only one. But if you want to, let's write it this way. What is the horizontal asymptote? Okay, so example one, notice the question now is in terms of a limit. It's not, here's a function, y equals x squared, and what is the horizontal asymptote, question mark, right? It's what's the limit as x approaches infinity. So as x gets bigger and bigger and bigger, what happens to the function x squared? And so much of these things can very quickly be answered using a graph, right? X squared is this happy face parabola guy, right? So as x gets bigger and bigger and bigger, does the function x squared like plateau or flatten out at some value, at some limit, right? Is it approaching a fixed value? Is it approaching a limit? Well, if you know the graph, you think, well, as x gets bigger and bigger and bigger, it just goes further and further and further up and up and up. So the limit, which again, as we've said multiple times, the limit is the y value. So what does the y value do as x gets bigger and bigger and bigger? Well, y just gets bigger and bigger and bigger. So that limit equals infinity, right? In essence, you can just think about plugging infinity in, What's infinity squared? Still infinity, right? It's kind of like one of those, I love you, no, I love you, oh, I love you infinity, oh, I love you infinity squared, and that's like more. I love you infinity squared plus one, but really that's all just infinity, right? So once you go beyond infinity and beyond, you've just still are at infinity, right? So infinity is not a number though. We don't really like think of it as a value that we like, plug in like 2 or 7 or 12. But you can pretty much plug in infinity and kind of do the math in your head that way. But it more comes from like knowing what the horizontal asymptote would be. The parabola x squared doesn't have a horizontal asymptote. It just goes up forever. So the answer is infinity. What if I have the line negative 7x plus 13? Okay, notice negative 7x plus 13 has parentheses around it, whereas x squared, I did not put parentheses around it. If I wanted to put parentheses around it, go back in black. I could do that. It's fine to do that. But when it's just like one function with like one term, like a monomial, you won't usually see them do that, but they could. So you'll notice sometimes I have parentheses, sometimes I don't. If it's more than one term, like negative 7x plus 13, you have to have parentheses around it if it's a limit question. Okay, that's how you need to write it. But what happens as x goes to infinity here for negative 7x? Well, as x gets bigger and bigger and bigger, y goes where? And what's supposed to happen is you go, oh, well, this is a linear function. It has a negative slope. The line goes downhill from left to right. So as x gets bigger, y goes to negative infinity. And I've taken a long time to answer these first two questions. Hopefully this video is going to get faster and faster and faster because I'm doing a lot of explaining here in the beginning, and each one of these should just go quicker and quicker and quicker, hopefully. Again, if you need to make a picture, sketch a little line in your head. Oh, plus 13, that's y-intercept, that's up here, and negative 7, well, that goes down. So if you think about the graph, negative 7x plus 13, right? There we go. As x gets bigger and bigger and bigger, y goes down forever to negative infinity. Again, if you try doing the math again, plug in infinity. Plug it in. What's negative 7 times infinity? Well, that's technically negative infinity, right? Because it's a negative number times infinity. Again, you can't technically do this. Infinity isn't really a number. It's a concept, right? But in a way, you can kind of cheat it, right? Plug in infinity, and negative 7 times infinity is negative infinity. Plus 13 is still negative infinity, right? Plus 13 is pretty insignificant to the size of negative infinity. But looking at the graph is really how you tell. So you'll notice in examples 3 and 4, I've shifted gears all of a sudden, and instead we're going to negative infinity is my limit value. So the title of this section is Limits at Infinity, or the limit as x approaches infinity. But you can sometimes also be asked, what's the limit as x approaches negative infinity? You can make x smaller and smaller and smaller and smaller, right? So looking back at the parabola graph that's at the top there by example 1, right? As I go to the left, right? See, negative infinity is back this way to the left. What is y doing? Y still goes up, right? If you were to plug negative infinity into the function, right? Negative infinity squared would mean negative infinity times negative infinity. And what's a negative times a negative? A positive. Infinity squared, still infinity, right? So for the parabola, right, both arms of the parabola go up. In Algebra 2, you talked about this exact same concept. I know you did, because you either had the fabulous Miss Squire, or Miss Thurman, or Miss Cundiff, or the amazing Mr. Minor. And I know in Algebra 2, because I taught Algebra 2 when you guys were in Algebra 2. So if you had the okay Mr. Quirk for Algebra 2, then we did this same thing. We talked about the end behavior of polynomials. So the end behavior, it's either going to be up on the left and up on the right, or up on the left and down on the right, or down on the left and up on the right, or down on the left and down on the right. So it's like the end behavior is up and up, or it's up and down, or it's down and up, right? Or it's down and down. Like those are only 4 things that can happen with the end behavior of a polynomial. And that's all these questions about limits and infinity are really asking. Is it's a different way to ask end behavior questions. And with my class, I always would just say the end behavior is up and up, and I would have them draw arrows. But it might have been if you had Mr. Ortman, because the Ortman, man, he don't play. He might have even said as x. As x goes to infinity, y goes to infinity. And that's basically what we're writing here. What's the limit as x approaches infinity? Or in this case, it was negative infinity. Sorry. Um, y is also infinity. I don't know if I'm making this more complicated than it needs to be. Plug in negative infinity in example 4. What's negative 7 times negative infinity? Well, that's positive infinity. What's positive infinity plus 13 more? Well, positive infinity. What's another way to do that is think in terms of the graph. Think in terms of the line. The line has a negative slope, which means it goes down. From left to right, it goes down. But if you walk backwards, right, if you go to the left, the line goes up, right? It's like one side of the same coin, or 2 sides of a two-sided coin, or maybe it's like I think it meant maybe it's a 3-sided coin, but you're only looking at one side of it or something. I don't know. Anyway, there's 4 examples. Hopefully those are the longest ones. Does that seem pretty simple? If you were allowed to use a graphing calculator, this would be really easy, because you could look at the graph very easily and be done. But this is where AP Calculus gets kind of tricky, because they like to ask questions where you don't get a calculator. Now this year, AP Exam 2020, things changed. And the way they set up the test for the AP exam this year was you didn't have to have a graphing calculator for any of the questions, but you were allowed to use one. So it's kind of like the ACT, right? They tell you all of these questions may be answered without a calculator, but everybody uses a calculator. So that kind of makes me think they didn't really ask a question that was this straightforward. These questions are really easy with a calculator. So how can we make them more tricky? Well, maybe we just pick a more tricky function. How about I stay here 5 and 6 for a second? Notice these both have to do with ln of x. So again, if you get a calculator, you type in y equals the ln of x. What's better than that is the ln of x function just looks like this. You can see it in your head. This is why it's very important that you do these graphs in algebra 2, you do them in pre-calculus, and then you have them memorized. You know what a line looks like. If the line goes down, you know what that looks like. If the line goes up, you know what that looks like. Parabola, happy face parabola, sad face parabola. Being able to look at the function and know the graph is huge. It will save you so much work and time and stress in calculus when you just know the graph. So I can just draw this graph very quickly, put a sketch of it down. And now what happens to the natural log function? There we go, 5 through 8. As x goes to infinity, as x goes to infinity, as x gets bigger and bigger and bigger, what does y do? Because that's what limits are all about. It's what the y value is doing. Notice the y value goes up. Now the natural log function, it does slowly go up and up and up and up and up forever. It doesn't go up as fast as a parabola does, or maybe even as some lines do, right? A line can be steeper than a log graph, but it does go up. 5 is infinity. What's the limit as x approaches negative infinity? Now something gets kind of tricky, okay? Negative infinity, as I approach negative infinity, that would mean go to negative 1, go to negative 10, go to negative 7 billion, go to negative 10 trillion, go to negative, bigger and bigger negative infinity. What is the blue curve doing as I go to negative infinity? You look back here and you'll notice there is no blue curve, right? The graph isn't doing anything as x goes to negative infinity. Okay, so example 6, all of a sudden things got a little quirky, and that we have an answer that is not infinity or negative infinity. So far, all of the answers have been infinity or negative infinity, right? But for example 6, we have a DNE. As x goes to negative infinity, the natural log function doesn't exist. It's not there. There isn't a limit. Now, questions 7 and 8, actually only number 7, I answered on the other video from a long time ago. What's the limit as x approaches 0 from the right? So we have a one-sided limit. And notice 0 is where natural log has a vertical asymptote. So what happens as I get closer and closer and closer to 0 from the right? Right, the blue curve is going where? Down, 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 down to negative infinity. Right, that question's been answered before. What happens when I approach 0 from the left? So the left side of 0, you're over here like negative 1, negative 0.5, negative 0.1. What is the blue curve doing on the left side of the asymptote? It's not there. So these two questions, 6 and 8, the left side of the natural log function doesn't exist. There isn't a left side to it. So you can't answer that question. Number 7 was technically a vertical asymptote question, right? Notice it's 0. It's not infinity or negative infinity. So the infinity and negative infinity questions, those are basically like horizontal asymptote questions. It's a weird way to have horizontal asymptotes, is to say what's happening as x approaches infinity or negative infinity. And speaking of horizontal asymptotes, okay, these are two pretty big examples that do show up in calculus from time to time. Like real talk, in this year we didn't have on the AP exam multiple choice questions, but I have seen this multiple choice question before. What's the limit as x approaches infinity of the arctangent function? And it's multiple choice. And there's no calculator. This is a no calculator question. Because this literally just comes down to, have you heard of arctangent? Have you spent any time with it? Do you know what it's doing? And the arctangent function, this is now at least the third time this year, maybe more than that, but this was also on our last video about horizontal asymptotes. The arctangent function has two horizontal asymptotes. One of them is at pi over 2. The other one is at negative pi over 2. Okay, so like this question number 9, arctangent, that's kind of a terrible A right there. I'm gonna try it again. Question number 9. This is literally like a Why did I put negative infinity over -2? I'm really sorry about that. I screwed up that graph there, right there. See that? Come on, erase, please. Negative pi over 2. Sorry, I know you saw me write that and you're like, what is he doing? Boo boo. Question 9. This question, it's literally like a 5-second question. It actually takes you longer to bubble it in than it takes you to know the answer. This is one of those like you just have it memorized answers. Okay? You just have it memorized. It's pi over 2. As x goes to infinity, as x gets bigger and bigger and bigger, arctangent has a horizontal asymptote at pi over 2. This is basically just asking you, what is the horizontal asymptote for the arctangent function as x gets bigger, 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 right? Bigger and bigger. Question number 10 is definitely a different question, right? Question number 10 is talking about inverse tangent. But is that what makes it different? No. What makes it different is it says negative infinity, okay? So first of all, you notice I used inverse tangent on one question and I used arctangent on the other. That's because I want you to know that they're the same and it could be either. Notice on question 9 I used parentheses. On question 10 I did not use parentheses around the inverse tangent function. They don't have to be there. So on question 9 I didn't have to have parentheses either. Notice on question 10 I used parentheses around the x, but on question 9 I didn't. I could have put arctangent in parentheses x. Okay? On number 10, I could have left the parentheses off the x. And our inverse tangent x is the same as arctangent. Okay? So I just trying to show you like different flavors of how they can ask the same damn thing. But what is the limit as x approaches negative infinity, right? As x gets smaller and smaller and smaller, as x goes to negative infinity, this is negative pi over 2. Okay, so questions 9 and 10. Like I said, I have seen question 9 as a multiple choice question on the AP exam where you don't get a calculator. And there really isn't anything you can do to figure that out. It's something that you just like know it. You have it memorized. Okay. And so I'll ask it again over the course of next year. And if it comes up by the AP exam, hopefully you'll have remembered by then, right? Negative pi over 2 and positive pi over 2 are the horizontal asymptotes for arctangent. Okay. We're almost done, I promise. This video is just about over, isn't it? What about e to the x? E to the x is exponential growth. E to the x is the inverse of the log function ln of x. So what happens as x goes to infinity? As x gets bigger and bigger and bigger and bigger, what does y do? Y goes up and up and up and up. It's infinity. The answer to 11 is infinity. What is the limit as x approaches negative infinity of e to the x? Again, this question, and this type of question could definitely be on the AP exam. There had even been a free response question similar to this because what we will get into at the end of BC Calculus is a bunch of stuff about series. A series is where you add numbers together. And so in the series section, they will throw in some e to the x's and stuff every now and then because they're geometric, whatever that means. But it means fun things can happen. And so this is, again, question 12. It's just, there isn't really any math to calculate. The only way you could calculate math would be to have a calculator and you would type in -10, -100, -1000, right? And you would notice, oh, these values are getting closer and closer and closer to something. Well, if you get to use a calculator, put it into y equals, right? Just graph e to the x and you'll see, oh, it's this. Oh, as x goes to negative infinity, there's a horizontal asymptote at the x-axis. So what is the limit as x goes to negative infinity of e to the x? Or what is its horizontal asymptote as you go backwards, as x gets smaller? And it's at 0, right? So limits at infinity have to do with horizontal asymptotes. As I go to positive infinity, e to the x doesn't have a horizontal asymptote, just like question 1. If you can rewind your mind to question 1, right? What was the limit as x approaches infinity of x squared? It was infinity. It's kind of like this part right here, right? This is like half a parabola. Now, e to the x and x squared are not the same graph. Okay, the parabola is different. But still, it's the same idea. As x gets bigger and bigger and bigger, y gets bigger and bigger and bigger. As another way to think of it, plug in infinity here, right? What is e to the infinity? E times 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 e, right? Forever and ever and ever. Well, that's got to be infinity. But what's e to the negative infinity? This is where it gets tricky, okay? Because a negative power, remember, a negative exponent means you reciprocal the base. That's what that means. Those are the same. E to the negative infinity is the same thing as 1 over e to the infinity. And so now you don't have e times e times e times e times e, which is infinity. You have 1 over e times 1 over e times 1 over e. And if you just pretend for a second that e is equal to 3, right? Because it's actually 2.7. So what's 1/3 times 1/3? Well, that's a ninth. What's a third times a third times a third? That's a 27th. What's a third times a third times a third times a third? That's an 1 over 81 or 181st, right? And then it becomes 1 over 243. And then it becomes 1 over 3, I don't know, 43, 349, something, 3 something. What would happen here is I would hope you would go, oh, well, those numbers are getting smaller and smaller and smaller, right? It's like we're getting more and more and more and more and more people, and we only have one pizza. And so we have to cut it into smaller and smaller and smaller and smaller and smaller pieces. So horizontal asymptotes, limits at infinity. Okay, we almost done? Goodness gracious. Look, we finished page 1. How long did that take? You guys can see the time at the bottom. I can't. What's the limit as x approaches infinity of 1 over x? These last examples are going to go real fast. I promise. You're almost done, right? Okay, this is the same thing as what is the horizontal asymptote, right? What is the horizontal asymptote? And what's happening here is you might go, oh, this is a rational function. And the horizontal asymptote for a rational function followed those 3 rules where we compare the degree of the numerator and the degree of the denominator. And if the degree of the numerator is less than the degree of the denominator, and in this case, 0 is less than 1, we know that the horizontal asymptote is always equal to the x-axis, which is the line, right? Y equals 0. So the horizontal asymptote is y equals 0. So what is the limit as x approaches infinity of 1 over x? It's 0. So the question is not being asked in terms of the words horizontal asymptote. It's just limit as x approaches infinity. Again, if you plug infinity in, think this is the same idea that I just mentioned with the e thing. It's like cutting a pizza into more and more slices, right? You have one pizza, and if only one person is there, you get to eat the whole pizza. So you get one whole slice, right, Mary? You get one whole pizza. But if 2 people are there, now you each get a slice. You each get a half. If 10 people are there, you each get 1/10 of the pizza. If 1,000 people are there, you each get 1,000th. So this number gets smaller and smaller and smaller. 1 over x goes to 0. And it has to do with the degree on top being less than the degree on the bottom. Example 14, look, the degree on top is 2, the degree on the bottom is 3. What's the limit as x approaches infinity? 0. Same rule as 13. I just made it look more fancy. Now 15, kind of weird. Look, it looks like the same question, except it's negative infinity. So how do these degree rules work when you have negative infinity or positive infinity? They actually work the same. If we could graph this thing, right, and we did this graph on the last video that was like 14 hours long. There was a vertical asymptote at 0, a horizontal asymptote at 0, and the graph, let's do it in green, was like this. Back to red now. So you see, as x goes to negative infinity back this way, it still has a y going to 0, right? The horizontal asymptote is 0. So if I plug in negative infinity, in for x, it's still like cutting the fraction into more and more and more slices. So it does approach 0. It just approaches it from the negative side of 0, right? The graph is going up towards 0, but its a limit at negative infinity, right? So this is why this section is called limits at infinity. Because technically you never get to infinity, right? But if you could get to negative infinity, if you finally got to the edge of the universe, it would be at 0. Okay, so 13 and 15, they're not really the same question, but they sort of are, okay? Again, what's the degree rule when they're the same? Question 16, 3x squared over 6x squared when the degrees are the same? Everybody raise your hand. Let me see, I'm going to call on you. Yes, you can answer. It's a ratio of their coefficients. Well, very good. So 3x squared over 6x squared means the answer is 3/6. The horizontal asymptote would be at 1/2. 1/2. 3 over 6 reduces to 1/2. because the degrees are the same. Okay. 17. 7x plus 13 over 3x plus 9. Oh, those are kind of cool looking numbers. Oh, look, it's 7 over 3. Like, even though it's negative infinity, it would still be the same thing. Okay, the horizontal asymptote to the left and the right of these rational functions is the same number. Now, there is a time, kind of like arctangent, remember where it had like two different asymptotes? There are some weird functions that can have two different asymptotes. Those we go left and right, those matter, but I'm not concerned about that right now. We're not in class to kind of do all of this, so I'm sort of skipping that example and may come back next year. Hey, what happens when the degree on top is bigger than the degree on the bottom? That was when we said there was no horizontal asymptote. There was no horizontal asymptote. That means there's a slant asymptote. That means the asymptote is diagonal, which means the graph at that asymptote is going up and up and up in some way. Okay. In this case, the slant asymptote would be a linear function. We would do long division and do all that, and maybe we'll do some long division when we get back to school. But for right now, it just doesn't have a horizontal asymptote, right? It goes to infinity, or it could be negative infinity. Like if I put a negative on top, then the asymptote would have a negative slant to it because I have a negative slope. So it would be negative infinity as I go to the right, positive infinity as I go to the left, just like example 2 and 4. You go back up and look at 2 and 4. But here with the positive 2x squared over 3x, it's infinity. Now, can you write d and e? Technically, it is d and e, right? When we say the limit is infinity, that means the limit doesn't exist, right? There can't be a limit and it also be infinity, right? Infinity is the complete opposite of there being a limit, right? Infinity is like, oh, I have a credit card. I can buy everything I want. That's not how it works, right? You have a credit limit on a credit card. You can only spend so much. So I'm basically, I think, done. Yeah, there's just two more. So what I did here with these last two is I just sort of started getting a little bit more quirky because, again, AP Calculus, they don't necessarily always give you polynomials, okay? An example 13, 14, 15, 16, 17, 18, those fractions were fractions of polynomials. With polynomials, we can use the word degree. So like on 17, the degree of the numerator is 1, the degree of the denominator is 1. On 18, the degree of the numerator is 2, the degree of the denominator is 1, right? But when you look at 19, it's got an e to the x in the denominator, which means it doesn't have a degree anymore. So the rules of degrees, they can kind of be expanded a little bit into including, it's more about which one grows faster or slower compared to the other. So in this case, like the x plus 2, that does go up and up and up, right? The line x plus 2, it increases, just like 7x plus 13. But the thing about 7x plus 13 and 3x plus 9 is they increase kind of in the same way because they're both lines. And that's why their degrees being the same matters, okay? And you get this 7 over 13. In AP Calculus, they like to kind of church it up and make it creepy. I thought I was erasing those once. Didn't happen. So here's my line. What does e to the x do? Again, this is why it's so important that you have these like kind of just basic concepts of these graphs down. E to the x also increases like a line, but it increases a whole lot faster. Okay, if we superimpose these two graphs on top of each other. Okay, the line, and the exponential function might do like this. Maybe I should try to draw that again, sorry. Like the line is above the exponential function for a while, but then eventually the exponential function like takes off, right? The exponential function is growing faster than the line. What that means is the line, it grows slower. So when the numerator grows slower than the denominator, that's like our example 13, 14, and 15 that you see right here, right? When the numerator grows slower than the denominator. Because see, when you plug in infinity, infinity plus 2 is infinity. But e to the infinity is like more infinity, right? It's n beyond infinity. So this is technically going to 0. This limit would be 0. And that's tricky. It's definitely trickier than like 13 and 14 and 15. So it's not about looking at the degree so much because e to the x doesn't have a degree. But what matters is that x plus 2 does not grow as fast as e to the x. So again, what's happening is the people are coming to your party, right? And each person like might bring a pizza, or maybe they bring half a pizza. But all the people at the party are eating the pizzas faster than they can arrive. So as you go to infinity, right? Remember, infinity is a huge, humongous number. As you go to infinity, what happens is the numbers of pizzas can't keep up with the numbers of eating, right? We're cutting the pizzas into more and more and more and more slices. Oops, which makes it go to 0. Question 20, last one, we're almost done. This question was actually in I have not seen this on the actual AP exam, but there was a question similar to this on a practice test that I have. And it wasn't worded quite in this way. It was tricky. It was a multiple choice question, but it asked you like which of the following would give you a limit of 0. So I kind of just gave the answer away here, but that's what we're looking at. Again, e to the x, it might even grow faster than x plus 2. Actually, probably not, because x plus 2 like might, but eventually it's going to outrun the e to the x, the line. So again, the numerator here, ln of x, does not grow as fast as the denominator. The denominator grows way faster, right? An exponential growth function grows very, very, very fast. So what's happening is the numerator gets bigger and bigger and bigger and bigger and bigger and bigger, faster than the denominator can keep up. The denominator gets bigger and bigger and bigger and bigger, faster than the numerator can keep up. So this function is going to go smaller and smaller and smaller and smaller, right? And if you could put this into a calculator, right, ln of x divided by e to the x, you would see that it would approach the x-axis. It gets smaller and smaller, closer to 0. But without a calculator, that's not as easy, right? So hopefully this is kind of making sense. This is a very conceptual thing, limits at infinity. There's not a lot of math to really do. You just have to think about what's happening. And that can be tricky because, thinking means you have to like use your brain, and that means, you have to like wake up and wake up. So I've made some questions. There'll be a worksheet. The worksheet's going to have other review problems on it. Okay, it's not just limits at infinity, but I'm going to put some limits at infinity and then some other stuff on there just to review. Okay, sound good? Sounds good. How long is this video? Don't tell me because I don't know. I'm going to look it up right now.